Okay, hello everyone. Let's go through some questions on alkenes. All right, so let's look at the first question. So this ACJC question, right? Free radical addition is a mechanism used in the synthesis of some addition polymers. So alkene polymers will polymerize in the presence of a radical initiator. For instance, the synthesis of polyethylene begins as such, right? So which of the following chains could not have arisen from free radical addition? Okay, so for this question, you must be able to see a pattern, all right? So this is the pattern. So you can see there's an alkene over here, all right? Alkene over here, and this is another alkene. So this is where they are. If you think about it, it's actually here and here, all right? So which of the following chains could not have arisen from the free radical addition? So I can see that for A, if you look at it carefully, A probably you can see that the alkene were here and here originally. This one is here and here originally. So maybe I just draw it out first. So the alkene is probably like CH2 for the first one, double bond CHF, right? For the second one, the alkene is probably CH, double bond CH3 and Cl, right? C, I don't think I can draw an alkene because it's actually this is the pattern, right? But there are 3 atoms here. All right, so for this next one, for D, you can see that this is probably the alkene. So I'm going to just draw it out. So it's probably like a benzene ring, double bond, CH2. So if you could see a pattern, you realize that actually C would be the answer. This chain could not have arisen from the free radical addition. All right, so let's look at question 2. Chloroethene is reacted with iodine monochloride, which is ICl, in the presence of aqueous sodium nitrate. So there's actually Na plus, there's NO3 minus, and there's water. Okay, so these are this is what's present. What are the major and minor products? Okay, so you need to know for the chloroethene. Okay, maybe just draw it out first. Chloroethene is this chloroethene. Okay, the first thing that happens is probably ICl will actually react first. Okay, but let's see who's more electronegative. So Cl is actually more electronegative, so it will be delta minus, I will be delta plus. So the electron-rich region will actually go to the I, and then electrons go to the Cl. Okay, so there are actually 2 possible products that you might get. So if I put the I on this carbon, it looks like this, and then this becomes a carbocation. Okay, if I put the iodine, all right, I put the iodine or I in the other carbon, this is what it should look like. Okay, and this I over here, and this is a positive carbocation. All right, so which is the possible structure, since they want the major and minor product? Okay, so we're going to see which carbocation is more stable. Okay, so in fact, this carbocation is actually less stable. Okay, why is it less stable? Because of the Cl, which is actually electron withdrawing. So because it's electron withdrawing, it will tend to intensify the positive charge, all right, of the carbocation, and it become less stable. Okay, so this will not form so easily. So I'll say that this is the major intermediate. All right, so this intermediate is actually more likely to form. So if I look at all the options, I want to make sure that it's the I on the Cl. So you can see that, yeah, so based on the options, right, A seems like the best answer, all right? And why are the rest the minor products? Okay, so what happens next? Because water is in excess, water will be the main nucleophile to attack this carbon, and that's why you get OH over here. So the other possible nucleophile that could actually attack the carbon would be the nitrate, which is O, NO2, or it could even be the Cl minus. All right, so yeah, so these are the minor products. Okay, so why OH? Because water is in excess, right? Okay, aqueous solution. Okay, so yeah, A is the answer. Okay, let's look at question 3. The following compound is reacted with ethanolic sodium hydroxide. Okay, so which of the following is a major product? Okay, there's this thing called Say-Sev rule. Say-Sev rule, right? So what's Say-Sev rule? It says that the more substituted alkene, will be formed. okay, will be formed with elimination, Okay, so let's look at the first one. So if I take away I and a H over here, right? This ethanolic sodium hydroxide, so it's going to remove HX, the H and the halide, right? So if I remove the HI over here, I will end up getting the alkene on the side. If I remove the I from here and the H from here, okay, the H from this I and this H, this is where the double bond will be, all right? Okay, but which one is more substituted? This alkene, look at the CC double bond. There's one group here, two groups here, and three groups here. And for this CC double bond, there's only 1 and 2. The H are not counted, right? The H's, we don't count the H's here, right? So that means by more substituted. So this is di-substituted. This one is tri-sub. So this seems to be the more stable alkene, right? So definitely, this will be the answer. All right, yeah. So the rest, I don't see how this can happen actually. Okay, this is not going to happen because there is no hydrogen on this carbon, so you can't get and there's no hydrogen on this carbon. Both carbon doesn't have a hydrogen, so you can't get a double bond over here. Okay, so this one I think is wrong also because there's nothing happening over here, so I don't think that's the answer. Okay, so B is the best answer over here. Okay, let's look at question number 4. A comparison is made of the rate of electrophilic addition of bromine, right, to the following compound. So what you need to do is you draw the carbocations. So for S, T, U, and V, I already drew out the carbocation. So like for the first example, you actually would put there are two possibilities, right? So I'm just going to show you. You could actually put the Br over here, and this will be the carbocation. You could also actually draw the Br on the other carbon, which is this one, and this becomes the carbocation. But of course we will draw this one because this is a secondary carbocation and this is a primary carbocation. So secondary is more stable, we probably draw that. Okay, so we're going to draw S, do the same for T, U, and V for fair comparison. Okay, so how the reaction vary? So over here, you can see from S and T, the only difference is there's a CH3 group here. So CH3, S and T, this CH3 group is electron donating, right? And this was just a H. In fact, if you look at it, this is actually considered a secondary carbocation. Okay, because it's 1R group and 2R groups. This one is a tertiary carbocation. So tertiary carbocation is actually more stable because of the additional electron donating group that will help to disperse the positive charge. All right, so to me, T should be the most stable. Right, T looks like the most stable. So this will be the fastest. All right, so I'm going to put this too. All right, if you look at U and V, I'm going to compare U and V because this one I and Br. So there are two halogens here. So between I and Br, we know that Br is actually more electronegative and more electron withdrawing than compared to I. So because of that, the positive charge here will be intensified to a greater extent comparing Br and I, right? So it will be intensified to a greater extent. Okay, because it becomes more positive as the Br is pulling electrons. So this is the least stable. So V will be the least stable, is least likely to form, and it'll be the slowest rate. All right, yeah. So that's why I put V as the slowest over here. So the answer for this question would be A. Okay, let's look at question number 5. When propene reacts with iodine monobromide in the presence of concentrated sodium nitrate, a mixture of products is obtained. So of course, I know there's actually sodium nitrate and also there's water, similar to just now that question. Okay, so again, Br is more electronegative than iodine. So delta minus, delta plus. So the electrons here will go to the I first and then go to the Br. So you'll form the more stable carbocation. So to form the more stable carbocation, I think you have to form the secondary carbocation. So you put I over here and this is plus. So this is a secondary carbocation. So I'm going to look at all the options. I want to see one with I on the first carbon. So I only see it over here. Can you see that? So this is definitely a possible major product. Okay, this is definitely a possible major product, because the next part is where the nitrate, okay, will actually attack the carbon cation, and you form C. All right. Okay, let's look at question 6. Which of following hydrocarbons would give the same organic product upon oxidation with hot acidified KMnO4? All right, so I'm going to just count the number of carbon. All right, so let's take a look. When this part breaks, 1, 2, 3, 4, 5. So a 5-membered ring. So it's going to look like this. 1, 2, 3, 4, 5. So this will be COH. This will be COOH. All right, and there will be a side chain over here, which is this one. All right. Okay, let's look at this one. If I oxidize this and oxidize this, how many carbon will there be? 1, 2, 3, 4, 5. So in fact, it's going to give you the same thing. 1, 2, 3, 4, 5. COH on this side. COH on this side. And the double this alkyl group is over here, which is actually the same thing, because you just, if you flip this one, you flip it, you get this. Right? So which of the following will give the same organic product? 1 and 2 definitely. Okay, let's try to draw 3. If I oxidize these two, how many? These two double bonds. Let's look at the longest carbon chain here. 1, 2, 3, 4, 5. All right, so which means actually you get the same thing. In fact, you will still get back this one here. You see that? 3, 4. Okay, so 1, 2, 3, 4, 5. So this becomes COH, COH. So, and this actually is the side chain here. So it's the same thing. So actually it's 1, 2, 3. Right? That's for question 6. So let's look at the next question. When propene reacts with aldone monobromide, which of the following could be a likely intermediate? Okay, so in fact we did something like that just now, right? So let me just draw it up. So I can draw the alkene, the propene. So I draw a double bond over here. So with I, Br, again, Br is delta minus, I is delta plus. So the same concept. Okay, which of the following species could be a likely intermediate? I'm going to just draw the more stable carbocation. So I'm going to put an I over here. All right, I draw the secondary carbocation. So this is what it should look like. So which one does it look like? It's probably going to be C. Let's look at question 8. A hydrocarbon on heating excess hot concentrated acidic KMnO4 produces this compound. So I like to always look at the number of carbon first, right? So let's check. 1, 2, 3, 4, 5, 6. All right, there's 6 carbon in this chain. So let's figure it out. Let's check. 1, 2, 3, 4, 5, 6, 7. Right, so I don't think this is going to be the answer, because there are 7 carbon here. Okay, let's try about it. How about this one? 1, 2, 3, 4, 5, 6. Yeah, so this is definitely possible. When you oxidize 2, you're gonna get C double bond O, CH3, CH2, 1, 2, 3, and you get the C double bond OOH. Okay, so this is actually the same as this. So you need to have 6 carbon, right? So let's try the next one. 1, 2, 3, 4, 5, 6. Right, so if oxidize this, in fact, you still get back the same thing over here. So the answer must be 2 and 3. 2 and 3. Okay, so this is definitely going to be C. Okay, let's look at question 9. When propene reacts with bromine in the presence of excess potassium nitrate, what are the 2 major products? So it seems like this type of questions are kind of popular. So let me just draw propene again. So over here, if you add bromine, right? So again, if I add bromine, you still form the major product as you're going to form the more stable carbocation. So this is the first thing you should be drawing. Right, put the Br over here, and this becomes a plus. You get a secondary carbocation. And the next part, right? So I'm going to look out for answers where I have a Br at the end. So yeah, I don't see. I think this one. Yeah, I see Br here. This is on the middle. Nope. This one could be possible. because it's at the end. This one is out, and this one doesn't have a BR, right? So just check these two. So what are the possible nucleophile that can attack the carbocation? Definitely it could be this, which is the NO3 minus, or it could even be the Br minus that was formed over here, or the last one, it could be water, H2O. Right, so yeah, so these are the possible nucleophiles that could actually attack the carbon. So let's see, yep, I can get this and I can get this. So this is wrong, B is wrong because this is a H, right? So this out. So the answer is D. Okay, let's look at the next question. Limonene can be obtained by a series of organic reactions. So this is the Diels-Alder reaction. Okay, so they already showed you what's happening. So I hope you can see that actually this pi bond, right, actually goes here. Let me see if I can draw it. It forms a bond over here. Okay, this is the one, and hopefully you can see that this pi bond actually forms here. Okay, it joins to that carbon. With me? All right. Okay, so what would be the product formed when the following diene and alkene reacts? So I want you to be able to see a pattern over here. So in fact, this is the same thing. This one will go to this carbon, all right, and the electrons here will actually go to this carbon. You see that? So I'm trying to draw it out. This is what, and then after that, you will see that because electrons goes here, this will form a double bond. All right, so I want you to be able to see that over here, this electrons will also go here, right? So maybe what happens is it's going to be something like this. Okay, this is original. All right, so now you have this part over here. So that's where this is the new bond that's formed over here, and this is the new bond that's formed, and you form a double bond here. All right. So in fact, if you look at it carefully, and there's still a line over here, there's one more bond over here. So I'm going to stick it out. Okay, so that's what it should look like. All right. So that's what it should look like. So if you look at all the options, it looks as if the answer is going to be A. Okay, let's look at question 11. Let's look at question 11. Which statement is not correct? So this is an electrophilic addition with bromine. They give you two possible scenarios. So you can get actually when the Br, you can put a Br here, and then you get carbocation. All right, so there's resonance. Electrons can go here, and you form the carbocation on this carbon, the first carbon. Right, then the Br minus will attack, and you can get a 1,2 or 1,4 addition product. All right, so let's look at whether they say which statement is not correct. So for the first one, the overall rate order is second order. Yes, it's correct. This is correct. Why is it correct? Because this is a slow step. So slow step will be, you can write the rate equation. Rate equals to K. Okay, so this is what the rate equation will look like. Right, so it's going to be second order. Okay, because they have one Br2 and one diene. Okay, the carbocation intermediate are resonance stabilized. Yes, so electrons can delocalize to form this structure. So this is actually a resonance arrow. So it's really resonance stabilized. This is correct. Okay, so the 1,2 addition product when HCl is used. So what happens when HCl is used? So when HCl is used, what you're going to get is, you can see that this delta minus, this is delta plus, and the electrons will go to the H first. So you're going to form a carbocation, but you must form the more stable carbocation. So in fact, the H will actually go to this carbon, the H will go to this carbon, and this will become a carbocation. And this actually is a secondary carbocation. All right. Then the next step is the Cl minus. All right, will attack this carbocation, and the end product will be something like this, with a Cl over here. So since they drew it like that, they put a Cl on the side. So this is taken to be wrong, and so the answer is C. All right. If you add ICl, it doesn't matter. So I and Cl on either end like this is totally fine. All right. Okay, let's look at question 12. Okay, beta carotene is oxidized by hot concentrated SVAC K-4. So all the double bonds will actually break. All right, oxidative cleavage, and you get many products. So they say out of all these products, how many of these products contain a ketone functional group? So I'm going to just show you where I'm going to oxidize all the double bonds. There are a lot of double bonds that will be broken. Okay, so for example, like this one over here, okay, this is actually going to be oxidized to carboxylic acid here, and this also be carboxylic acid. So this is called ethane diet. So ethane diet is easily oxidized to CO2. Okay, yeah, it's easily oxidized CO2. Okay, so you realize that all these are the CO2. So I'm just going to cross out. All these will actually be CO2, which you don't really have to care. Right, all these will be CO2. So, but over here, if you look at this product here, okay, let me just draw this part out. It's going to be double bond O, OH, C, CH3, all right, and then a double bond O, right? So this is your ketone. So in fact, you get how many ketones over here? You get 1, 2, 3, 4. They are the same. Okay, you get 4 ketones. And over here, if you break the double bond here, all right, this product, both sides will give you ketone, right? Both sides over here will give you ketone. It's going to look like this, right? This will be a ketone, and this also will be a ketone. All right. Okay, so you have ketones on this side and this side. All right. So anyway, you have a ketone, and in fact, this molecule and this molecule, if you look at it carefully, once you oxidize it, it's actually the same thing. All right. So you have a ketone here. So 1, 2, 3, 4, 5, and 6. Okay, so this side will also give you ketone and ketone over here. So, but out of all the molecules, 6 of them will give you a ketone functional group. Right, so let me just show it to you. So it's something like this. So we say we count it as 2 here and 4. So out of all the molecules here, 6 of the molecules will give you a ketone functional group. Right, so the answer is B. Okay, let's look at question 13. Malic acid is used in the food industry for stabilizing drugs. It's a cis isomer of butene diuric acid. So I'm going to just write out nicely. So this is butene diuric acid. It's a cis isomer, so it's probably going to look like this. Right? Okay, so what is the product when it reacts with cold dilute asphalt camphor? So this one is whereby the alkene will become a diol. Okay, diol. So essentially what you're doing is you're just breaking the double bond here, all right, and you're going to add in OH and OH, right? So that is the final answer. So you look out for the one with 2 OH, so it probably is going to be A. Yep, okay, because of the word cold. Cold means mild oxidation. Okay, let's look at question 14. How many chirocarbons are formed in a major product of the following reaction? Okay, so you're gonna add ICl. So you realize that when I add ICl, right, I and Cl, delta minus delta plus. So the double bond will always attack the I first, and then it goes to Cl, and you must draw the major product. Okay, so you must always form the more stable carbocation. So the more stable carbocation is probably this one here. So I'm going to draw, I put an I over here and I over here, and this will be the carbocation. This is the more stable carbocation. So for this case, I'm going to put the I over here, and this will be the carbocation. All right. Okay, so because it's going to be more stable, it's a tertiary. Okay, so the next thing is the Cl will attack the carbocation, Cl minus, and this is your product. Cl here, and the Cl here. All right. Okay, so they say how many chirocarbons are formed. In fact, you look at it carefully. This is a chirocarbon, because there's no plane of symmetry, right? Think about it. If you try to cut it this way, right? Yeah, so this side and this side are actually different. Can you see that? Okay, so it's a chirocarbon. So I'm going to say there's actually another chirocarbon over here, of course. And actually this is also chirocarbon, and this is a chirocarbon, right? Can you see that? Okay, so, but is this a chirocarbon? So this is a bit tricky. Is this a chirocarbon? In fact, if you think about it, actually there's a line of symmetry over here, which means this side is the same as this side. So which means this carbon is not chiral. No, not chiral. Can you see that? Okay, so it's not chiral. So which means yeah, so you only have 4 chirocarbon. So that's why the answer is C. Okay, let's look at question 15. When pen-2-ene reacted with coal dilute as Km4, what will be the major product? So coal, again, I told you, is mild oxidation. So I'm going to look out for a diol, and I think this is just straight away you can tell. Okay, so 1, 2, 3, 4, 5. So you can see that this is your pen-2-ene. Right, so let me just draw again. 1, 2, 3, 4, 5. Pen-2-ene is like this. So when you add coal acidified potassium manganate, this is your product. You're going to add OH here, and you're going to add OH here. Alright, so this is definitely C. Alright, okay, so let's look at the next question, 16. Which alkene on reaction with steam at high temperature and pressure in the presence of phosphoric acid could produce an alcohol containing a chiral carbon? So you're actually drawing the alkene becoming an alcohol. Alright, so you're going to follow Marconico's rule again. So the first one I'm going to put the H over here, and this is the more stable carbon. In fact, Marconico's rule will show that this carbon has 2 H's and this carbon only has 1. So H goes to the carbon with more H's. So I'll put the H over here, and the OH goes to the other. Now the OH, right, will go to this carbocan. Right, so let me just draw it out nicely. So I'm going to just put in the OH. Okay, so this is the alcohol. Okay, for the second one, if this one doesn't really matter, it's symmetrical, right? So I just put the OH over here. Right, so chiral and chiral. Okay, for question, for option 3, it doesn't really matter where you put it, so I'm going to put the OH over here. So, but if you put the OH here and the H over here, right, you realize that this compound doesn't have a chiral carbon, because if you think about it, there's a H, OH, and this one has a line of symmetry passing through this carbon. So this carbon is not chiral, right? So in fact, the answer is only 1 and 2, right? So 1 and 2, B. Okay, let's look at question 17. Which of the following products or compounds react with HBr in addition reaction to form a major product that is chiral, right? A major product is chiral. So with HBr, delta minus delta plus, the H delta plus is the electrophile. It will go to the double bond. I mean that the electrons from double bond will attack the H first. Right, and then you have to draw the major product. Okay, draw the major product. So just follow Marconico's rule. I think this one you can follow Marconico's rule. So the H will go to this carbon because it has more hydrogen. This has 1, the other carbon has none. So follow Marconico's rule. This is what you get. Br. Okay, so in fact, if you think about it, this carbon is not chiral. This carbon is not chiral because this is CH2, CH3, CH2, CH3. Okay, so this is not chiral. Okay, let's look at the second question. So if I draw it based on Marconico's rule, this is what you get. Here, I put the Br here. Okay, H and Br. Right, so is there a chiral carbon? Yes, this is a chiral carbon. Right, okay, let's look at 3. Okay, follow Marconico's rule again. I put a H here, can you see? Put a H here because this carbon has more H's. It's 2. Right, so the Br will go here. This CH2, CH3, and this is CH3. So is this carbon chiral? It's not. Okay, it's definitely not chiral because it's CH3 and this CH3. This carbon here is not chiral. Alright, so yeah, so the answer, it seems like it's only 2. Right, so that's the answer for question 17. Okay, let's look at the next question, 18. Compound X is reacted with hot concentrated. So there's elimination to form isomers. So I'm going to just draw, I can take a OH from here and a H from here. Right, so with the first compound would look something like this. Alright, first one. Okay, I take away OH and H from here. Okay, the other one I can take away is the OH and the H from here. So this is where I'm going to draw the double bond. Alright. Okay, the last one, I'm just going to take away the OH and a H on this carbon. Right, so there's a double bond over there. So I'm going to draw it out. So double bond over here. Okay, so in fact, one side here, this is drawn like that. Can you see that? Okay, so this is where the double bond is. Right, this is a double bond. Right, so I'm just drawing the same thing. It's just I just turn the line. Okay, so what is the total number of isomers formed, including stereoisomers? So this compound would have cis trans. So I would say there are 2 and no chiral center. This compound would not have cis trans because both sides are CH3. So it's only 1 and there's no chiral center. And over here, this one doesn't have cis trans. It's also 1. Right, doesn't have cis trans because there are 2 H's over here. So altogether is 4, right? In fact, there's no chiral center in all the molecules. Alright, okay, let's look at question 19. The following reaction occurs via 3 steps. Alright, so let's see how it works. And this is the product. Okay, and this is the product. Alright, okay, so if I'm going to add HCl, right, let's figure out if I'm going to add HCl. Imagine this is the double bond, delta minus delta plus. Imagine this electron from here goes to the H. Okay, let me try to draw it out. Okay, and if I try to follow Markovnikov's rule, I chose this because it can follow Markovnikov's rule. So the H will go here, and in fact this will become the carbocation. The H will go here, alright, because this carbon has H, the other carbon doesn't. Right, follow Markovnikov's rule. This is what you get. Alright, okay, the next step, what happens is this electrons here will go to the plus over here. Right, so when that happens, you're going to form a bond. Okay, you're going to form a bond. So this is what you're going to draw. Okay, so maybe just to give you an idea, where is this line? So in fact, this this line here, right? Okay, is actually this line here. Okay, let's check whether how does it make sense. Say this carbon number 1, carbon number 2, number 3, number 4, number 5, number 6. All right. So this is actually carbon number 1, number 2, number 3, number 4, number 5, number 6. Can you see that? That's where it joins. All right. Can you see that? So if I have to number it nicely after that, it'll be like, say this 7, 8, 9. So this is like 7, 8, 9. All right. So 9 actually becomes the carbocation. And the next step, all right, the next step is the Cl minus that is being formed. Will attack this carbon. All right. So carbocation, right? So that's why you get the answer. Okay, so based on my drawing, I just showed you. So that's why the answer is 2 and 3. Okay, the answer will be C. Okay, so these are the drawing. Okay, let's look at the next question. Question 20. Compound X reacts with hot acetate potassium manganate to give 3 organic products. Which compound could be X? So let's take a look. I'm just going to draw it out so you can see what's happening. So this is the ketone. Alright. The next one, okay, this is a bit tricky, but I'm going to draw the carboxylic acid over here. Alright. Then there's a CH2, CH2, CH3, and a double bond O here. Okay, I'm going to draw the last one. This one will look like this. A minute. That's right. So this one here, I will just draw it this way. So it's C double bond O, OH, CH2, C double bond O, OH. Okay. So if I try to work backwards, I work backwards, right? So when this was oxidized, it gave you this. So if I try to work backwards, you can see that this was originally an alkene, CH2, CH2. This was CH3. This was also an alkene, right? Can you see that? So I'm just trying to combine these two together. Alkene, alkene over here. And this is CH2. So I guess this part is a bit tricky. So I think it fits nicely into all these actually. Over here, can you see that? So this part here is a bit tricky because this part was actually originally an aldehyde. They put here an aldehyde. Is that? This was aldehyde. But aldehyde could actually be aldehyde. So aldehyde will be oxidized to a carboxylic acid. So this is definitely possible. Right, so your oxidative cleavage of the double bonds, you get these products. And the last part is the aldehyde get oxidized to a carboxylic acid. That's why the answer is B. Alright, okay, let's look at the next question. Question 21. A sample of ethene was added to a solution of bromine and sodium chloride. Which of the following products is not likely to be found? Okay, so how you look at it for this type of question? Very simple. Okay, the first idea for alkene, right, it always reacts with the halogen, which means like bromine. So we know that this is exactly the first step, right? Delta minus, delta plus. So this is always the first step. So you definitely form a carbocation with a Br. Right, so if you look at all the options, in fact, I'll just say D is definitely the answer because D is the one that doesn't even have a Br. Okay, so that's why 21, the answer is D. Okay, let's look at question 22. Which compounds give one product when reacted with steam in concentrated? So this is actually an alkene becoming an alcohol. Alright, okay, so let me just try to draw it out. So the first one, I probably can draw it this way. If I add the OH here, CH3, okay, which give only one product. Okay, whether you put the OH on this carbon or you draw the OH on the other carbon is actually the same thing. Okay, because this molecule is totally symmetrical. Okay, so they say which compound give only one product when we react the steam. I say yeah, this one only give one product, so they are the same. So yeah, this one. Okay, for this also the same concept. In fact, you get either OH here or OH on the other side, but it's still the same because it's yeah, you flip it 180 degrees, it's the same thing. Okay, so they're the same, so you only get one product. Okay, one product. For the last one, this one you can actually put an OH over here, or you could actually put the OH over here. Alright, and in fact they are different products, so this one will be considered as 2. Alright, so which compound give only one product is definitely 1 and 2. Okay, so 22, the answer is A.
Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.